Hi, hello students. Welcome to Unacademy. Crack GATE computer science with us, top educators, quality content, great learning experience. Let's crack GATE CSE. Crack GATE and ESE with India's largest learning platform, none other than Unacademy. Get Plus subscription and access unlimited live and recording courses from India's topmost educators. About myself, Srinivasarao Sir, having 17 years of GATE experience in the subjects of DBMS and OS. I also had certifications in DBA, Cisco, MCSA, and Red Hat Linux. Also had industry experience as a database admin and a system admin. In the journey of GATE, many of the premium academies got single and their double digit ranks by having DBMS, CN, and operating system content, which I taught. I taught in many premium academies across India like Gate Forum, the Gate Academy, Vishwa Educate, Time, and Made Easy too. An Academy Learning app, if you get it installed, you will get top class courses from top class educators. What will you get after installation of an Academy app? You will get daily live classes where you can discuss with the faculty members any sort of doubts and clarify in the class itself. And live tests and quizzes, as you know that mock tests are benchmark to crack any kind of GATE examination. So an academy also provides live test and quizzes. And about structured courses, all the courses are predefined and structured manner as per the curriculum of GATE and other public sector undertaking examinations. It also provides unlimited access where you can get recording lectures as well as live lectures. So learn with the top educators to get the top quality of education. As far as CSIT concerned, there are many courses are available. As a part, I'm going to deal with database, networks, and operating system. There are two kinds of subscription as a student. One you can join in 12-month subscription, the other you can join in 24-month subscription. If you use my promo code, you will get some concession up to 10%. This is a 24-month subscription. The fee cost is 30,000. You will get it for 27,000 by applying my promo code. So this is the schedule I want to follow for the month of July, where you will get complete course of DBMS as per as GATE pattern. And some classes I am teaching on YouTube, which are theoretically, and the other classes I am discussing on student learning app of Unacademy. There you will get a discussion about previous year GATE questions and multiple choice questions. This is the schedule for the month of July. Now, we are going to discuss about today's lecture, schema design. It is in the form of different parts. Today we are going to learn about part 1 of schema design. Now, in the series of schema design lectures, we are going to learn about like functional dependencies and attribute closures and the super key and alternate key derivation, decomposition mechanisms and minimal covers, membership test, and the very important concept that is nothing but normal forms. So this is the score structure of schema design, which is in the part of different series. Now today we are going to learn about functional dependencies. What is a functional dependency? Before you learn about the functional dependency, let me give you some introduction about schema. So what is a schema? As I told you in the previous lecture that in relational model, everything is an object. Here also, a schema, we are going to call it as it is object. It is an object, identifies uniquely. And one more important thing is that every schema associated with functional dependencies. That means without functional dependencies, the schema doesn't exist in the real world. Therefore, what is a mandatory? Every schema is associated with some functional dependencies. Why? Because functional dependency is the concept to derive keys. Keys are going to provide non-redundant data. How it provides non-redundant data, how to derive keys, we will learn in the series of schema design lectures. Now let us learn. After learning about a schema, schema is nothing but a relation, which is nothing but an object, which is uniquely identified. Now what is the meaning of functional dependency? Let us see the definition. Here, there is a schema R, also called as a relation I am calling, because as per as a chord rule, you have to call everything is in the form of relation or table only. Now in this case, relation R has two attributes like x and y are having some kind of tuples. Now we want to prove that there is a functional dependency x tends to y is existed in the above relation R when the following condition is existed. What is the condition, friends? See, this is the condition. What is the condition here? Observe carefully. This condition is applicable for all the tuples which are in the concerned relation. So here, what is the condition is, if tuple 1 dot x column is equal to tuple 2 dot x column, then you say that tuple 1 dot y equal to tuple 2 dot y. So this is the condition we want to follow for all the rows. When this condition is satisfied, we will come to know that there is a x tends to y is satisfied. Now, which means if x uniquely determines y value, then we can understand that y functionally dependent on x value. Okay, friends, how to prove? Don't just get fear by seeing the definitions. This is the language of Henry F. Code, who is the author for database management system. We are trying to put it in the form of some kind of shortcuts using tricks. What is the trick I want to give you? Just observe it. Now this is the example. I want to prove a functional dependency A tends to B. Here I want to say that LHS is A and B is considering as RHS. Now this LHS also called as determinant. This RHS we will call it as dependent. See friends, next time onwards you have to call LHS as a determinant, RHS as a dependent. Don't forget this. Now you want to prove A tends to B. This is what he is asking. A implies B. What is the meaning of A implies B is? See that first we want to see the determinant value is unique or not. So in this case, 1 is unique for the first time, hence it satisfies automatically A implies B. Observe carefully. This is the trick I want to give you according to the definition of the previous slide. Now, once again you look at this. This 1, once again it is coming. It's not unique. Why? Because 1 is already available earlier. So we want to prove the condition. What is the condition? The condition is like this. If t1.x is equal to t2.x, then t1.y is equal to t2.y, which means whenever the determinant value is repeated, then automatically dependent value has to repeat. Hence, when 1 is repeated here, we would like to see that the 2 must also be repeated. So we understand 2 is repeated here, hence we feel that A tends to B is satisfied for the second row. Now come to the next row, 3. 3 is a unique where it is not available in the earlier rows. Hence, whenever determinant is unique, you don't worry about the dependent, it is satisfied. Now come to the next row, that is 5. 5 is a unique. Whenever determinant is a unique, we don't worry, it is satisfied. Next, another one is very important. When this 5 is repeated, then what you need to look at, you need to repeat its corresponding determinant value against the dependent value. So here, as 7 is given for the value of 5 and 7 has to be repeated. Hence, in all the cases, A tends to B is proved. Hence, we come to know that A tends to be implied in this case. So, I want to give a flow diagram here that how you could able to prove this kind of functional dependencies. Now you see, I want to say that A implies B, I want to prove. Two cases I am giving you. One case, A is unique. If A is unique, friends, you can guess it. What is satisfied? A implies B is satisfied. Now come to the second flow that A is not a unique, it is a redundant. Redundant is nothing but duplicate value. So come to this. Whenever this 1 is repeated, what has to repeat? The corresponding value of the 1 has to repeat. Therefore, whenever LHS is repeated, then we want to see that if LHS is repeated, then you need to have two conditions. What is that? RHS must be repeat. So B is repeat. When B is also repeated, in this case also we say that it is A tends to B. So as far as first two tuples concerned, you will understand whenever 1 is repeated, then what is has to repeat, 2 has to repeat. So whenever LHS value is repeated, then RHS value has to repeat. For example, if B is not repeated, then what you need to do? The condition is a fail, and so we will say that A not implies 2. That's it, friends. Using this flow, you can easily understand whether the functional dependency is existed in the relation or not. Clear? Now, using this flow diagram, we'll look at examples. Now you see, there is a relation R which consists of A, B, and C attributes. The data is mentioned as 1, 2, 3, 4, 2, 3, 5, 3, 3. Now you see, he is asking which of the following functional dependencies does not hold. The meaning of does not hold is nothing but the FD is not satisfied against the given data. So let us check the first option, A tends to B is implied or not. As I told you, to prove the A tends to B, A is the determinant for us and B is the dependent for us. So like this, he is asking you to prove the first one, A implies B. So in this case, we want to see that A is a unique value or redundant value. So look at the flow diagram which I shown in the earlier. So I want to prove A tends to B. To prove the A tends to B, you see that A is unique or not. If A is unique, automatically it is satisfied. If A is not unique, then you need to look at the other two conditions. So let me check. A tends to B. As the first value, it is a unique. So you can say that A tends to B is satisfied here. Now we want to see that 4 and 2. 4 is a unique value and so you can say that this is satisfied here. And 5 is the unique value, you can say that it is satisfied here. Hence friends, we understand A tends to B is proved why A values are unique. Clear? Now let us look at B tends to C option. What is a B tends to C? This time B implies C here. That means B value is supposed to be unique. If not, it has to see that its dependent is repeated or not, right? So 2 is unique, hence B to C is satisfied. But this 2 is repeating here. Whenever 2 is repeating, what has to come? Its dependent value has to come. So it is repeated. Henceforth, that is satisfied up to the second row. Come to third row. 3 is a unique value which is not existed in the earlier B values, hence automatically it is satisfied. Hence B implies C is also satisfied. If you look at AC tends to B, what is AC tends to B? You observe carefully friends, AC tends to B here is AC together is your determinant. It is a composite determinant, not a simple determinant. Why? Because multiple values are depends on A and C column. This time AC implies B means we want to look at A value and C value together to prove this functional dependency. So let me write here A value and C value which is implying to B. That means AC together is implying B. So what are the values? A value is here 1 and C value is here 3. A value here is 4 and C value is here is 3. A value is a 5 here and C value is a 3. We want to write the B values 2 here, 2 here, 3 here. So now let us check the first one, AC is unique or not. So 1, 3 is unique, hence it is satisfied, AC tends to B. Next row is 4, 3 which is not existed earlier. I am looking at AC combination together, hence it is also satisfied. I am looking at next row 5, 3. 5, 3 is not available earlier rows, hence as LHS is unique, it is also satisfied. So we come to know these three dependencies are existed in the relation R. Now let us look at BC2A. So this time BC to A we are observing here. A value here and B value here and C value here. First let you write BC values. So 2, 3, 2, 3, 3, 3. And what is the A value, friends? 1, 4 and 5. Now we want to say that this BC together is implying this A value. Now you see that 2, 3 is unique. We don't mind. It is satisfied. But you observe carefully. 2, 3 is coming here once again. Whenever this 2, 3 is repeated, the given value earlier for 2, 3 as a 1, hence 1 has to be repeated, but instead of 1, 4 is not given. Hence we can say that here BC2A is failed. Hence our answer is which of the following functional dependencies does not hold an OR is nothing but BC2. Well friends, this is how you have to prove whether LHS is a simple or LHS is a composite. Now let us move on to next. So the relation R consists of three attributes x, y, z with the following data. He asks that which of the following is satisfied. So same rules we want to apply. First of all, I am going to check with option A, that is x, y to z. Now you observe xy value unique. Xy value unique. Unique means 1, 4 is not repeated. And 1, 4 or 1, 5 not repeated. 1, 4, 1, 5, 1, 6 are not repeated in the next. Therefore, xy to z is satisfied. He is also asking you to prove z to y. Let us see. Unique value, but you look at carefully here. When z value 3 is repeated, z against value is a 5 is mentioned here. So 5 has to be repeated here. As 5 is not repeated, hence we can prove that z to y is failed. Even though the first production is correct, second production is invalid, and so we can go for this is the wrong option. Now let us move on to second one, yz to x. What is a yz to x? So 4 2 is unique, observe carefully, and 5 3 is also unique, 4 2 is unique, 5 3 is unique, 6 3 is also unique, 2 2 also unique. Hence, this is satisfied. What about y to z? So y 4 is mentioned unique, 5 is a unique, 6 is a unique, 2 is a unique. Hence, both are satisfied. So let us look at option C also. Yz to x, it's okay, it's proved. X to z, we want to prove two conditions, right? What is x to z? 1. Again, whenever 1 repeats, the one given corresponding value is 2, 2 has to be repeated. Here, as 2 is not repeated, and so we will feel that this is invalid. Therefore, this option is also wrong. Let us look at option D, xz to y. What is xz to y? So, xz value, first value is 1 2 unique, 1 3 unique, 1 3. This is very important. Xz value. You want me to write? I will write here. Observe carefully. X by z, and we want to prove xz to y. What is x value? 1. Z value 2. What is given for that? 4 is given. Again, what is the x value? 1. What is the z value? 3. What is the value is given? 5. As 1 2, as 1 3, as they are unique, it is satisfied. Now I am writing once again for the third row 1 and 3. Whenever this 1 3 is repeated, please observe carefully. So what has to come? 5 has to come. But what is given for this? 6. Hence we will say that this is invalid. So hence the correct option is this. Okay friends, I hope so now you got understood how to identify the functional dependency is existed in the relational schema. Now let us look at into another one. So relation R consists of three attributes, namely ABC, with the data mentioned like this. So we want to prove option A is possible or not. Let us check A to B. So A value 1 unique satisfied. Whenever A value is repeated, its corresponding B value has to repeat. So it is repeated, correct. The next value 2, it is a unique, therefore it is satisfied. Whenever this value is repeated, then its given corresponding value has to repeat. Hence A to B is a pakka, it's proved. But what about B to C? Let us understand. B value initially given as a 1 and C value is given as a 1. Now whenever this 1 is repeated, what has to come? This 1 has to come. But what is given? 0. And so we come to know that this is valid. Now let us check this. A not implies B. This is wrong. Why? A implies B as far as here. Because in the option A, we proved that A tends to B. Hence, this option is also wrong. This option is also wrong. Now we will check B not implies C. Obviously, B not implies C. Why? Because initial value of B is a 1 and the corresponding value of C is a 1. And here 1 is repeating for the next row, so 1 has to come here, but instead of 1 what is a mention? 0 is a mention. So instead of 1 0 is a mention, then we come to know that B is not implying to C. That's it friends, this is how you can prove functional dependency. Okay, now there are two varieties of functional dependencies. One is a trivial, the other one is non-trivial. What is a trivial? What is a non-trivial? This is a very important subtopic in functional dependency. So what is a trivial? Trivial means is nothing but, as the definition given like this, where y is a subset to x, then it is called as trivial FD. Trivial FDs are always available in the relation. We need not bother. By default, they are get to be satisfied. Our main concentration is to always prove what? Non-trivial functional dependencies only. How to prove? We will see in next slide. So what is trivial? Now look at here. I am saying if beta is a subset or equivalent to alpha, that means every beta value is a part of alpha, and I will say that alpha implies beta. This is exact definition of trivial functional dependence. Therefore, let us check here. I am saying AB are the two attributes of a relation R which consist of some values like 1, 5, 1, 6. If I am writing A tends to A, observe carefully friends, I am writing different functional dependency this time. A tends to A. What is A tends to A? This is a dependent, which is nothing but RHS we are calling. This is a determinant, we are calling it as what? LHS. See the definition. If a beta is subset or equivalent to alpha, that means this RHS is a part of your LHS. Whenever RHS is a part of LHS, let me write, this is a shortcut. If RHS is a part of LHS, then you can call it as this is what? Trivial functional dependency, no doubt. Now, as far as this concern, it is a trivial. Now, let me write a few other. Why it is a trivial? Why it is by default satisfied? We will look at now. Now, let me write. If I am saying AB tends to A, this is also trivial. Why this is a trivial? Because this RHS value is a part of LHS. If I am writing like this, xy to x, now this is also trivial FD only. So what is the meaning of a trivial FD? If RHS is a part of LHS, then it is a trivial. If I am writing something like this, A tends to B, it is a non-trivial. Why it is a non-trivial? You can simply understand that your RHS is not part of your LHS. Hence it comes under into what? Non-trivial. This is how to identify trivial FDs. Why trivial FDs by default satisfied? Let me write an example here. As far as this concern, A and A are two attributes. A value 1 and 1. What is A value here? Same, 1 and 1 only. That means every beta value is subset to alpha value. Every beta value is a subset to alpha value. Henceforth, every trivial functional dependency by default satisfied. You need not check them. So two important points I said. One point is what is a trivial FD, and the second point is what is a non-trivial FD, and third important point, how trivial FD by default existed. As I said, from this example, you will come to know that trivial FD is existed. Why? Because every beta value or RHS value is a part of your LHS. Okay, friends. Now let us move on to non-trivial. I already gave you definition of non-trivial there. What is a non-trivial? Non-trivial FD RHS value is not part of what? LHS. This is being proved like this. What is that? Please observe. Let me write here. Now I am writing here. Please observe, friends. I want to say that x tends to y is the functional dependency. Now you will come to know that whether it is a trivial or non-trivial. It is a non-trivial. Why? Your RHS attribute set is not part of LHS. Hence it is a word non-trivial. This you can prove it like this. What is that? X intersection Y. Two attributes I am mixing now, X and Y. If X intersection Y, if there is no common, that means it is a pi, then we can say that this X tends to Y is a what? Non-trivial. That's the definition. What is that? If X intersect Y is equal to pi, then it is what? Not trivial. You want me to prove trivial? I will prove. See this. For example, I am writing X tends to X. This is a trivial. Why? Let us write its condition. What is that? Please observe. X intersect X is equal to what? It's not a pi. X intersect X is equal to X, which is not is equal to pi. Then you will come to know that it is a what? Trivial functional dependence. This is another rule to prove triviality and non-triviality. Okay. Now come to the point. Trivial functional dependencies are two varieties, complete non-trivial, the other one semi-non-trivial. What is a complete non-trivial? What is a semi-non-trivial? Like this. It's a complete non-trivial. Now if you look at semi-non-trivial, observe carefully. X tends to XZ. What is X tends to XZ? If I split the RHS, observe now, X tends to X. One more is also there. What is that? X tends to Z. So in this is the trivial functional dependency. Why? RHS is a part of what? LHS. This is a non-trivial functional dependency. Why? Your RHS is not part of LHS, which means semi-non-trivial FD consists of half part trivial, half part non-trivial. Altogether, it is called as semi-non-trivial functional dependency. Well, friends, complete non-trivial means you don't find any kind of that beta is subset or equivalent to alpha, but in semi-non-trivial, one production you will get it as a trivial, the other production you will get it as a what? Non-trivial. Okay, let us prove some examples on non-trivial. Now I am writing there is a relation R which consists of ABC and some dependencies are given that A tends to B, B tends to C, AB tends to C, BC tends to A tends to A, B tends to B, and AB tends to A, and AB tends to B. Now you observe them. How many are trivial? How many are non-trivial? Let us say the first one you see that A tends to B. If you consider RHS is a not part of LHS, hence it is a non-trivial. RHS is a not part of LHS, non-trivial. This is also non-trivial. This is also non-trivial. But you observe carefully this and this RHS is a part of LHS. RHS is a part of LHS. RHS is a part of LHS. Hence they are called as trivial MDs. Okay friends, one more example. I am saying X tends to YZ, X tends to XY, X tends to X, Y tends to X. Now, how many are trivial? How many are non-trivial? We want to identify from this. Now, you could easily say the answer. What is that? First one is trivial. Second one is RHS is not part of LHS, non-trivial. Now you observe the third one. This is very important. One is part, one is non-part, and it is a what? Semi-non-trivial. X to X, directly it is a trivial. So this is how you will prove trivials, non-trivials, and semi-non-trivials. Again, I am repeating for semi-non-trivial. RHS is a part of this. RHS is a not part of this. Hence, RHS has one is a trivial, one is a non-trivial. Altogether, we will call it as what? Semi-non-trivial functional dependency. Okay, friends. Now, let us move. Armstrong axioms, also called as inference rules. What are they? Now I said that some dependencies are existed in the relation, some are not existed in the relation based on these rules only. Behind every functional dependency production proof, there are some rules are existed. I said that please observe carefully. I say A tends to A is existed, A tends to B is existed. This is a one functional dependency. This is a one functional dependency. We call this is a trivial. We call this is a non-trivial. How would I able to say? They are able to say only using this inference rules, also called as Armstrong axioms. There are two varieties. One is the sound rules. In sound, there are very famous three rules are there. That is reflection, transitivity, and augmentation. What is a reflection? If y is a subset or equivalent to x, or x is a superset or equivalent to y, then I can say directly that x tends to y. Which FD this is, friends? Trivial. Why it is a trivial? Your RHS is part of your LHS. So LHS is superset or equivalent to RHS. Clear, friends? That's why reflection rule always existed when you are proving trivial functional dependency. You are said that it is a trivial. Why it is a trivial? Because of reflexivity rule, reflection. If I know a value, I can write a value. That's the meaning. If I know a value, I can write a value at the right hand side. Clear? Now, what is the transitivity? So, when x tends to y is given and y tends to z is given, I can write a new production such that x tends to z. What is the meaning of that? When x implies y and y implies z, then x automatically implies what? Z. This is what is the production of transitivity. And what is the augmentation? Augmentation is nothing but appending the attributes at LHS. For example, there is x tends to y production is given. Then he is asking you to produce a new FDs by augmenting z. Now, the given production is x tends to y. Now, if I add this z here, if you add z at LHS, that z I can add at RHS. See the beauty of augmentation, friends. What is that? Earlier z was not there, only x tends to y is given. By augmenting this z at LHS, you can get it for RHS. So what is the production now? xz to 1 is z, one more xz to y. So augmentation always gives you semi non-trivial functional dependencies. Why? If you observe, this is a trivial and this is a non-trivial. So you will get two parts at the right hand side. One is a trivial, one is a non-trivial. So three important rules. Reflexivity always gives you trivials. And augmentation always gives you semi non-trivials. Which means RHS has got one is a trivial production, the other one is non-trivial production. Okay, friends? Let us learn complete rules. These rules are also knowingly or unknowingly are available or existed in the relational schema. Let us see. X to y and x to z is given. I can combine RHS. How you combine RHS? X tends to yz. Simply combine RHS side. Now, decomposition at RHS. Opposite to the previous. X tends to yz is given. I can write such that x tends to y union x tends to z. Clear, friends? And don't think that xy tends to z is equal to x tends to yz. Clear, there is no concept of associativity. In FDs, you need to understand here no association. What is a no association? Same thing I am writing. xy tends to z is not equivalent to x tends to yz. Clear, friends? Now, pseudo transitivity. What is that? X tends to Y is given and WY to Z is given. Now I am giving you help. What is that? R is W, X, Y, Z. Now we want to derive a new production using this. So now if X tends to Y is given, let me write X tends to Y. If I add W, because W is belongs to your R, if I add W here, you got this W can be added using a augmentation like this. Now what did you get? By just augmentation this W, I can get this value at RHS. Hence a new production is XY tends to YW just by taking X tends to Y by augmenting this W value. Now continue. The other production is given. What is that? WY tends to Z. Now what is the new production you will get, friends? XW to WY, WY to Z. So what is the new production you will get? XW to Z. That's it, friends. So pseudo transitivity is applicable like this. Augmentation I am doing, transitivity I am doing. So I am able to produce a new production that I can write here. Well, friends, again I am repeating. By taking X tends to Y, augment any of these attributes. I am augmenting W so that I can map to this production XW. When you augment this W, the W you can write at RHS side as the rules of reflection and augmentation. So XW tends to YW. Already this production is given as WY tends to Z, hence I am going to get XW to Z. And last accumulation rule you are very familiar. What is that? X tends to YZ and Z tends to W. I can write X tends to Y and Z and W. Y transitivity X to YZ, X to Z, it is nothing but X to Z, and Z to W. I can write that X to W. So what do we understand, friends? To prove any kind of functional dependency, either sound rules or complete rules will come to the picture to prove whether the dependency is existed or not. So that's why these are inference rules which are following by schema design, whether the functional dependency is proved or not proved. So why these are called as a complete rules? Complete rules are completely depends on sound rules. Hence it is called as complete rules. Sound rules are the basic rules. So complete rules depends on this sound rules only. Well, friends, so what I want to tell you is sound rules, whenever you talk about the sound rules, they are the basic rules which can derive any kind of functional dependencies. Some are can be proved using completion rules. That's why complete rules depends on sound rules. So sound rules are the basic rules. Okay. Now let us see that what are the functional dependencies are existed. The functional dependencies are existed like this. I'm saying the employee has number, name, job, department number. Now you say employee number has got some data field, employee name has got some data, job also given something, department number also giving something. So now we want to prove that how many functional dependencies are existed in the employee schema. Listen carefully, friends. First let us check. So I am writing few you can follow remaining using the same concept. I'm taking employee number to employee number. Is it a trivial or non-trivial? It is a trivial. Why? Because your RH is a part of your LHS. You need not check the trivial FD. By default, they are existed. Time waste. Now, if I am saying like this, employee number to employee name, is it proved or not? Let me check. Employee number, first one is unique. 2 is given unique, which is not appeared earlier in the employee number. 3 is unique, 4 is unique, 5 is unique. Hence, this is satisfied. And that too, this is a what? Non-trivial. This is a trivial. This is a non-trivial. Okay? Why? RHS is not part of LHS. Let me write employee name to job. So let us look at employee name data. Chaitanya unique, Vanu unique, Sri unique, Akshay unique, Gaurav unique. As LHS is a unique value, hence it is approved. If you look at the fourth one like this, I can write job with department number. So observe carefully, manager unique, department number 10 is given, analyst unique, department number 20 is given. Analyst is very important, repeating. When analyst is repeating, what has to repeat? It's a given value has to repeat. It is repeated here and proved. And manager is repeating here. What is the value you have to give? 10. It's repeated. Now analyst is coming once again. As analyst is coming, it's a given first value is 20. Hence, it is also satisfied. That too, it is a non-trivial. Let me write one more. Department number implies employee number. Is it true or not? Let us check. Now this time our concentration department number only. So 10 unique, 20 unique. This 20 is repeating here. So you have to look at in which column, friends? Employee number. Observe carefully. 10 employee number is a 1. Let me write otherwise like this. 10 employee number. This is a department number. This is employee number. Department number. This is employee number. Department number 10 is given. Employee number 1 is given. Department number 20 is given. Employee number 2 is given. Department number 20 is coming once again. What is given for third? 3. This is wrong. Why? As 20 is repeated, what has to come? Employee number has to also repeat. Hence, I will prove that this is invalid. This is not satisfied. Clear, friends? Finally, what do you understand? You can write the remaining also. You can write remaining like department number to job, department number to e-name, or employee number e-name to job, or employee number e-name to department number, same. Now, I want to give one important trick. See here. Employee number to department number is proved or not? Let us check. Okay. What is employee number? 1 unique, 2 unique, 3, 4, 5 unique. That means it is satisfied. But reverse. Department number not implies employee number, as we have seen here. That's why in functional dependencies there is no concept of what? Commutative. There is no concept of what? Commutative. What is the meaning of commutative? A tends to B may or may not equal to B tends to A. This is the example. What is that? As we satisfy this, but reverse is not satisfied. That's why it is a concept of not a commutative. So, as far as a functional dependency is concerned, you may also have the concept of as there is no association, there is no concept of commutative nature. What is a commutative nature, friends? A may be satisfied, but reverse. B may or may not satisfy to A. That means A tends to B may not equal to B tends to A. Clear, friends? Now, let us prove the very similar example like this. Find the functional dependencies which are existed on the above. Our intention is non-trivial. Let us prove. A tends to B is proved or not. A1, A2, new values, but here you observe A1 is repeated. When A1 is repeated, B1 has to come, but B3 is given, hence it is false. Now, A tends to C. A1 against value C1, A2 C2. Whenever A1 is coming, what has to come? C1. Okay, it is proved. And A2, whenever A2 value is coming, observe carefully. The A2 given value is C2, it is proved. And A3 is a new value which is not existed earlier, hence proved. Therefore, A tends to C is proved. Now let us check A tends to D is proved or not. So A1, the value of D is D1, proved because LHS is unique. A2, D2 is given because LHS is unique, but you observe when A1 is repeated, the D1 should come here. But D value instead of D1, D3 is given, hence it is wrong. Now let us prove others. B tends to C is proved or not. So B1, C1, B2, C2 unique, B3 is unique, B4 is unique, B6 is unique. All the B values are unique. When LHS is unique, you need not look at RHS. By default, it is satisfied. Okay. Now, same like B2D also will prove as B value is unique. And let us look at B2A is also prove as B value is unique. Now, let us see C tends to D is satisfied or not. Now C1 unique value, C2 unique value satisfied, but you observe C1 is coming here. When C1 is coming, this D1 has to come, hence it is a fail. Now you can do like this. C2A also you can prove. C1 A1, C2 A2, C1 repeating. When C1 is repeating, A value is coming. When C2 is repeating, A2 is coming. C4 is a new value and it is satisfied. You can also get through composite dependencies like this. AB tends to C. This time you need to look at AB together. What is AB together? A1 B1 unique, A2 B2 unique, A1 B3 unique, A2 B4 unique, which is not there earlier, A3 B6 unique. Hence you need not worry at the right hand side. So likewise you can prove multiples. Now I am proving BC tends to D. What is a BC? B1 C1 unique, B2 C2 unique, B3 C1 unique, B4 C2 unique, B6 C4 unique. And it is satisfied. Let us check CD2A is satisfied or not. C1 D1 unique, C2 D2 unique, C1 D3 unique, C2 D4 unique, C4 D4 unique. When LHS is unique, you need not look at RHS. This is how to prove number of non-trivial dependencies which are existed in the schema. Okay, friends. Now let us see the example. He asks you to prove only triviality. Which of the following is a trivial? I said, what is a trivial? Again, I am writing. Real FD nothing but RHS is a part of LHS. Simple. Non-trivial FD is nothing but LHS intersection RHS supposed to equal to pi. That means RHS is not part of LHS. What is semi-non-trivial functional dependency? Which is nothing but LHS will give you RHS. One is a trivial FD, one is a non-trivial FD. You identify PR tends to ST. S is not part of PR, T is not part of TR. Hence it is a what? Non-trivial. Come here. PR tends to RT. What is PR tends to R? It is a trivial. What is next one? PR tends to T. It is a non-trivial. Hence, this is your semi-non-trivial concept. Now come here. PS to S. What is S? S is a part of LHS. It is your answer. PS to S is your trivial FD. What about this? PSU to Q. Q is a not part of your LHS. Hence it comes under into non-trivial. Well friends, these are the three rules you have to follow carefully to prove whether it is a trivial or non-trivial. Shortcuts, there's three. Clear? RHS is a part of LHS or not? If it is a part, trivial. If not, non-trivial. If RHS has got some trivial, some non-trivials, then it is semi-non-trivial functional dependency. I hope so you understood how to prove the functional dependency. Okay friends? Now, what are the applications of functional dependencies? Where are we using? So without functional dependencies, you cannot do any kind of further task. Why? Because the functional dependency will tell you redundancy is there or not. The functional dependency is also helpful in order to derive attribute closures. For example, I am taking student table. When you take the student table, student number, student name. I am saying student number 1, name is given as XYZ. That means for XYZ student, I have given number 1. If I am saying the student name like Abhi, then I am assigning a number to her. If I am saying Priya, now I am giving a number 3. So this is how the role exists. If I am saying that whenever I call Abhi, then who has to respond? The 2 has to respond. This is what is the meaning of functional dependency. So as many times I call Abhi, 2 has to respond. As many times I call Priya, and 3 has to respond. Whenever I call some XYZ, and 1 has to respond. This is how. For example, I say 4, the student name is Divya. Then as and when I call number 4, then you have to say that Divya only will respond. You cannot give this number to others. If I am calling number 5, I say that it is something like Sai. Now whenever I call SAI Sai, then this 5 has to come. This is how you can prove the functional dependencies, how they are existed in the relation. Well friends, let us move on to the next topic, attribute closure. Why we are learning attribute closure? Come to the previous slide. I said that the application of functional dependencies where we are using in construction of what? Closures. What is a closure? Don't worry by seeing a big and long definitions. I will provide you shortcut techniques how to identify closure. The closure is nothing but, as far as definition concerned, union of FDs is called as attribute closure. And functional dependencies are based to calculate attribute closures. Okay, which is designated with F plus. F is nothing but functional dependencies. Closure is nothing but closest set of attributes. So we will call it as that. Closest set of attributes to F is your attribute closure. Okay. Now there are some examples. So author is the schema table which consists of many number of attributes like this: author ID, author name, book ID, book name, publisher ID, publisher name. Okay. Now some functional dependencies are there. Author ID to author name to publisher name, book ID, book name, and other dependency. Book ID implies book name, publisher ID, publisher name, author ID, and there are many. He asks you to find the closure. So finding closure is nothing but you derive the closest set of attributes to every LHS. As there are 4 LHS, I am calculating closures for them. Okay. The first closure is author ID. So let me write the first author ID closure. AID closure. When I am writing AID, so use the reflection rule. What is the reflection rule? If you have some X value, that X value you can write. As I am finding AID closure, that AID is with me. So AID implies AID. And AID implies A name. So write down AID to author name. And one more. Author name implies publisher. So by knowing author ID, I would get author name. By knowing author name, I could get other attributes also. That is publisher ID, publisher name, and book ID, and book name. And continue. And book ID, if I know, I could get book name, publisher ID, publisher name, author ID. Already they are there, so I am not rewriting once again. So publisher ID will give publisher name as it is there with us. Book ID is there with us. Book name is there with us. Author ID is there with us. Author name is there. This is the close-up for author ID. Now let us write author name closure. You have author name with you. As in when you find the closure for any kind of attribute sets, the attribute sets are there with us. As I am finding a name closure, that a name is with us. So now you see, by knowing a name value, I would get publisher ID and as well as a publisher name and as well as book ID as well as book name and others. By knowing publisher ID, I will get publisher name and publisher ID will give you book name. I can write the book name here and I also come to know that author ID and also I come to know that author name. So I can write that author ID and author name here. This is the second closure. What is the third closure? Book ID. Now I am writing the third closure here. So book ID closure here. By finding book ID closure, book ID will give you book ID as well as book ID implies book name. So come to the previous slide, you will come to know that what can be written. So book ID will give you book name, book ID will give you publisher name, publisher ID, author ID. So I could write them. Publisher ID as well as publisher name. So these are the things I could able to write by knowing book ID. Now I can also write others. Why? Because by knowing publisher ID, as I know the publisher ID, publisher name, author ID, author name I can write. So therefore, still it is there. Publisher ID, publisher name, author ID, and author name. This is how to find the closures, friends. Okay. Now, what is the next publisher ID closer? So by finding publisher ID closer, take a publisher ID. So this is the closer. Publisher ID is with you, and you will come to know that publisher name. By knowing the publisher name, then you will get book ID, book name, and write book ID and book name. And by knowing book ID and book name, see, come back here. By knowing book ID, I could get the same set. I would get AID, get A. That's it, friends. This is how to find the attribute closer. We'll look at another example. Now come here. This is a simple example where you can understand easily. He is asking you to find the closures of A and closure of B, closure of C, closure of D. When I find A closure, A is with you, reflection. When I am finding B closure, B is with us, reflection. C is with you, reflection. D is with you, reflection. Now you see, by knowing A value, I could get B. So now I have the combination of AB together. By knowing B value, I could get C. Now C is with me. I could get D here. This is the closure of A. What is a B closure? By knowing B, I would get C. And by knowing C, I would get D. By knowing D, I would get A. This is a B closure. Now what is a C closure? By knowing C, I will get D. By knowing D, I will get A. And if I know A, I will get B. And what about D closer? By knowing D, I will get A and B and C. This is how to obtain closures. Very simple trick I am providing. Okay. Now come here. He is asking you to find a PQ closure. How are you going to find a PQ closure? It's very simple. By finding PQ closure, the PQ is there with you. So PQ here. So by knowing P value, as I know P value, I could write R and T. And as I have Q value with me, by knowing Q, I could get S. As R is with you, I know R, so I can write PS. So P is there, S is there. I have a QS, I could get T as well as U. So this is PQ closure. What is that? PQRSTU. So our answer is none. Let us go to another example. Now I want to find VW closure. So I said VW is there with you. By taking V value, I could write WX. W is there, I am writing only X. By knowing W value, I can write Z. So because I know Z, I can write X. X is there already. And I have, is there any combination of Y? So Z is X over, W to Z over, X, Y we want. As I do not have this, I cannot get this combination. As I have V, I can write WX. And what else I could write? You want to get ZY. What is the combination required? XY is required. As I do not have Y is with me, X is there but Y is not there. So this is your answer. What is that? VWXZ is your answer. Come to PR closure. What is the PR closure? So PR closer, I have reflection PR. Now by knowing P, I could get Q. I have QR now. By knowing QR, I could get ST. So I have P, T, and I do not have U combination, so that I couldn't get V. And so your answer is only PQRST. This is your answer. Now, what is false from the following? Now you see, this is true or not. CF closer I am finding. When you are finding CF closer, CF is there with me, and this CF, I got it. So by knowing CF, what are you going to get? So I could get G, I could get E. G and E. If you know G, what can you get? A. What else? So do you have AF combination to get D? Yes, A is there, F is there. So I could get D combination, write it. Anything else will you get? So we got D value, we got F value, we got G value, we got E value, we got A value. So this is your CF closer. A is there, and C is there, and D is there, and E is there, and F is there, and G is there. Okay, now come to BG closer. When I am finding BG closer, BG is there with us. So BG is there. What can you get? By knowing G, I can write A. If you have A and B combination, I could get C and D combination. Okay, by knowing C combination, I could get G combination. What else? We got A combination, G combination, and you want to get E. What is required? F is required. As F I do not have, I cannot write E now. I got G combination, I got C. Because I know C, I would get G. G already written. Now you want F combination. What is required? DE. As E combination is not there, you cannot get. Hence your BC closer is A, B, C, D, G. This is also correct. Now come to AF closer. What is AF closer? Now you see AF I have. So A and F. By knowing A and F, I could D. Write it down. Now what else? Can you get CD? You won't get CD. What is required? AB. As AB is not there, you cannot write CD. Now already I got this. F is there with me. And G you want. What is required? C. As C is not there, I cannot write G. And you want E. What is required? F. So I can write. As F is there, I can write E here. As I do not have G, I cannot write A. Once again, let us go back. So you want CD. What is required? AB. AB is not there. So this is already done. You want F. What is required? DE. So F I got it. You want G. What is required? C. C is not there. I cannot write. You want E. What is required? F. So E is there. You want A. What is required? G is required. So as D is not there, this is your answer. But he has given more attribute. Hence it is false. What about AB closer? Now let me write AB closer here. By finding AB closer, I have got AB. By knowing AB, I got C and D values. Okay friends, by knowing C, I could able to get G values. If I know G, I could able to get A value. So what extra is mentioned? A there, B there, C there, D there, G there. What extra he mentioned? F. You want to F. What is required? DE combination is required. So as I do not have E combination, this is my answer. and this is also false. Okay, friends. So now find the number of functional dependencies hold on relation schema R. This is the typical question. How we able to solve? Let us see. I am just to find the closure. Int is finding closures. I am finding a closure. What is a closure? A only. A gives you B, and I have B combination, I could get C. As I have C combination, I could get A. This is A closure. What is a B closure? The B closure is like this. I have a B. By knowing B, I could get C. By knowing C, I could get A. B, C, A. And other closure is C closure. By knowing C value, I could get A. A will give me B. So what the total number of, or find the number of functional dependencies hold? I can write like this: A to A, one dependency; A to B, another dependency; A to C, other dependency. Therefore, A tends to A, 1, A tends to B, 1, and A tends to C is another one. Now let us write same and B to B in this, B to C in this, B to A in this. Now here also you will get same story repeats: C to C here, C to A here, C to B here, C to C, C to A, C to B. This is how to derive number of functional dependencies of a given scheme. Well friends, let us look at the similar example. How many are whole? Same story repeats. What is the hint? The hint is nothing but find the closures. This is your hint. So find AB closure. When you are finding closure, find only for LHS, friends. That is also another hint. So AB closure and BC closure and C closure. What is AB closure? I have AB with me, I have BC with me, I have C with me. Okay, so AB will give you C, and I have BC combination. I could get A already present. As C is there, I could get B is already present. This is your closure of AB. Now BC, as I have BC combination, I can write A, all you got. Because of C, I could get what? B value. As I have CB or BC, both are same, I could get which value? A value. So your total dependencies, if I am writing completely, AB tends to A from the first, AB tends to B, and AB tends to C, and from the second one, BC tends to B here, BC tends to C here, BC tends to A here, third one, C tends to C here, C tends to B here, C tends to A here. These are the dependencies which are held on the above relational scheme. The hint for this question as well as another question is just by finding attribute closures for your LHS. By finding LHS closures, you will come to know that what are the functional dependencies are existed on the given R. These are all satisfied. The same way, the previous slide is also showing. Again I am the LHS closure I found, LHS closure I found, LHS closure I found. For example, if I am saying that does AB2D existed, then simply I will say answer is what? No. Why? Because it is not part of any of these dependencies. See this. It is not part of any of these dependencies, hence it is what? Not possible. Come to the next slide. If I am saying something like AB to C is possible. Now, Does AB to C implied or not? Now find AB closure, see that C is coming or not. What is AB closure? AB closure, I already found. AB closure gives you C, hence it is implied. I will say that. Answer is a what? Yes. Okay friends, this is the similarity questions of last two questions are based. Now, what is the application of attribute closure? The application of attribute closure is nothing but derivation of super keys. That super key is nothing but it is a superset of your candidate keys. Well friends, this is the end of functional dependencies and attribute closures. Subscribes to us, use my promo code Sankara for any kind of fees concession. Hit the bell icon for the latest notifications as well as join our Telegram group. Let's crack GATE CSE. Stay tuned to us for more lectures. Thank you very much.